start.
So it's a pleasure to introduce Kaiqi Yang, University of Miami, who's going to tell us about potential stabilization of body partners over complex fields.
Thanks for the introduction. Yes, I think yesterday Charles introduced the conics over real numbers, but this is a non-closed field. So this Galois group is simple. It's just a 0, 2. But right now, for this one, we consider a conic bound over non-closed field, more general one. Okay, so actually, this project is motivated by this famous example. Sorry, I don't speak French. Written by Bouville, Coletalin, Sensac, and Swinton-Dyer. The very important theorem is that they show there's a family of conic bundle of degree 4 that is not rational but stays irrational. And we have the theorem that that Kt, the transcendental field extension of K, 0, where K0 has a characteristic not equal to 2, and Ptx is a polynomial in that ring, and assume P is separable and irreducible and has degree 3, and view it as a polynomial in X with coefficients in K0t, and let X defined by this affine equation, where with variable x, y, z, t, and moreover, this at is the discriminant of t with respect to x, and they show that K0 variety x is stably K0 rational, and they give explicit rationality construction of this. Right? X times A3 is K0 rational to A6. Okay, that's the main theorem. Okay, that so the construction tells us, okay, this variety is stably rational. The next theorem by Iskowski tells us that if a conical bundle, standard conic bundle over K, if it contains at least 4 degenerate fibers geometrically 4 degenerate fibers, then X is not K rational. So that that completes the theorem that says it has 4 degenerate fibers. So that's not rational. And explicitly, they give this example, like they pick the polynomial x cubed minus 2. The discriminant is minus 3, defined over q, and that's important. And they showed that x times, actually here, there's a typo there. That's A3, should be A3, is K rational to A5. But I will say, moreover, I think it's due to Shepard-Barron that they showed, yes, the same variety times A2 is still rational. But if this variety X times A1 is irrational, is unknown. Okay. And in this example, the splitting group of this variety X is S3. And the the rationality construction for this one is like X. Well, they construct a torsor, and finally you have to show this torsor is rational, and then the torsor is the intersection of two geometrical integral quadrics in P7, I think, and it contains an irrational line that is not contained in the singular locus of X. And of course, this intersection of two quadrics is not a cone, and they project from this line, and that gives the rationality construction to show this is rational. Okay, so the question is, can we find other stably rational, non-rational conic bundle over P1 with other splitting groups? So that's why we want to find another example, or at least the splitting group is not S3. So for a standard conic bundle over P1 with n pairs of degenerate fibers, the splitting group is containing the well group of Pn or you could say this is a sign permutation group, and this is a sum product of Sn with z mod 2 to the power n minus 1. It's like this is a permutation part, this is a sign part. Okay.
Can you remind us what is
A splitting group is like you have the geometric Picard that you define over some field, and the minimal field containing all those defining equations, and you consider the Galois group of that field over the base field, and that Galois group is a splitting group. And in this case, the geometric Picard has rank n minus 2, n plus 2. So to find possible splitting group, we study the H1 obstruction that mentioned yesterday by Van, right? We try to compute this condition. So that's
so splitting group is a group of extension such that basically all these fibers becomes split. So like Picard group becomes into the n plus.
Yes, yes. Sure. Okay, that's one condition. And from there, since this is some conic bundle, so we know that this thing got to be a two torsion part. And we have this cohomology. So I think this is textbook stuff. So for every finite group G satisfy H1, so you can only if there's still two subgroups, G2 satisfy H1. Okay. I think this is easy. Okay, that's one condition. That's the H1 condition we need. And another one is like, say, for example, we have a surface, but it's not minimal. So we contract it, and we keep doing this until we cannot contract anymore. So we need this minimality condition. But here we're working over a non-closed field, so we need to mention this K minimality here. But okay, that's a geometric one. And we have another concept that is called the relatively K minimal, which means, okay, the G invariant, G is the splitting group. The G invariant part of this geometric Picard has rank 2. Okay, so if the degree is not equal to 8, which means it's not the P2, it's generated by the canonical class and the class of a fiber. And moreover, so for relative K minimal, but the non-K minimal conic bundle can only appear if its degree is equal to 3, 5, 6, 7, and 8. So it's like for degree 4, that's like they are the same, and for degree 2 or less, they are the same. So which means that's a very practical condition to check the K minimality, say for general cases. Like we have more and more digital fibers, degree is less, and we just need to check the G variant part. The rank 2, the K minimal. So right now here we fix. So in welcome of Dn, we need to find such groups, satisfy these two conditions. The first, you have to satisfy this H1 obstruction that I just showed. And another thing is have to satisfy this K minimality condition here, which means the G variant part of the Picard has rank 2. But here, actually, I should emphasize the degree we should have some conditions on degree. Degree
So
4.
when you say satisfy H1 as obstruction, you mean H1 is 0?
0. Yes, we don't have H1 obstruction. The cohomology are equal to 0. Okay, and try to develop some theory about those groups in general overarching. Okay, so first I just have some numerical test, do some numerical example. So for example, for well D4, here's the S3. There's only one, and that is the S3 that's used in the previous paper written by Colette Balance and Sackville, Switch and Dye. For example, is just this group. And for the next one, we will D5. Well, here in this case, degree 3. So the rank, the G rank part has rank 2, but we can't guarantee it's K minimal.
I think we can guarantee it's not K minimal.
Well, okay. That's fine. That's fine. But anyway, so let's start. Let's
It's a cubic.
yeah, it's a cubic, so you can. Next one, the web of D6. Okay, then you have a degree 2, and you have a bunch of stuff here. Oops. And also, like, only get up to web of D9. What about well, D10 or D11? Well, those groups are so huge that I can't run it on computer. And actually, that motivates what I'm gonna do next. But let's go back. See here. So here we see this is S3, and I try to find some general theory. So I think what is S3? Maybe it's like a symmetric group. It's like a dihedral group, or maybe it's a Frobenius group. And later we can see now here, say for example D3, S3 as a dihedral group. The next is D5. I should see D5 here. And if I see that Frobenius group, then I should have F5 here. So maybe there are some patterns there. Going. So let's go to the main theorems. Okay. So I just mentioned that when n gets larger and larger, the group structure, gets more complicated. You have more and more complicated group. I feel like finding it's impossible to compute it use Magma or other computer software. So I try to analyze those basic stuff. For example, for this, there's still some basic stuff. For example, for a group element in the web of Dn, it has a form where the last tau is in some permutation cycle, and first we have like a t, a signs, and we can also write it in another way decompose it according to their permutation cycle. So moreover, for this group element, we have a character that only counts how many signs we have there. Okay. So I will start from the very basics, the cyclic group, and also the proof is like originally we have to. I just try to originally I will try to compute the cohomology, right? Then I turn it into you solve a linear system over integer, and try to determine whether such integer solution exists or not. And that's the basic stuff. But anyway, this is the first one. Say let G the element in the web group Dn, and it has this form. And let lambda, the number of sign permutation cycles beta I with sigma beta I equal to -1, which means within this cycle, it has odd number of minus signs there. And then the H1 of such cyclic group equals to 0 if lambda equal to 0, 2, and otherwise it's 0, 2 to lambda -2. Okay, that's one thing. Okay, so I have this, conditions on cyclic groups. Then of course, I hope I have some control on those generators. Let's say, for example, for a cyclic group, if they satisfy H1 condition, that this is condition, and the beta is a sign permutation cycle in G with sigma beta equal to -1. It has all number of minus signs. Then the length of such cycle is less or equal to 2, and there is at most one such cycle within this group element. And up to conjugation, there are 3 types of generators satisfying this assumption. Like you have a C1, C2, C1, C2, with 2, 3, and the rest permutation cycles always have even number of minus sign, or you don't have such kind of stuff. The key idea is, maybe I should have. Say for example, you have C1, a CJ1, CJT, and you have a length n cycle. Okay, now you raise to power of n. So you will have C1, Cn if t is odd. And so right now, you have n cycles with odd number minus sign, according to the previous thing, which means since you need the triple cohomology, which means n has less or equal to 2. That's the main argument. Okay. So also from there, since we know the we have the H1 condition on those generators, and further analysis on those generators will tell us that for a group G satisfying both H1 and the minimality condition, then the G action on the set of degenerate fibers can only have at most 3 orbits. Because if you have more than 3, then you can find elements within such group has more than 3 sign permutation cycle with odd number minus sign, which give you obstruction to the H1 condition. Okay. So right now, say from those examples, I have examples with several orbits, and also I have some examples they only have 1 orbit. So if I just restrict to 1 orbit and see what's going on. And here is like a projection. Oops. This is like a PO is like a projection operator. The input is a group element, and the output is something like this. And here, Cn prime plus 1, because you want to stay in the well group of the n, right? So which means sometimes you need to another minus sign to stay in there. Because in total, you always need even number minus sign. Okay, and then first, and then I proved like 2 lemmas that first, this is the actual group, and the PL is a group homomorphism. And the projection, after projection, the image satisfies both relative minimality and H1 conditions. So that gives me more idea. It's like, say, for example, I have a group with large n, but according to this lemma or theorem, I can decompose it, right, into several pieces according to the orbit decomposition. But conversely, like if I have some groups, I know its action on some orbits. Can I combine them to get a large group with 3 orbits, but it's stay large with a large n?
That's a small question.
Yes.
You're constructing a group,
Yes.
and then for this group, you're going to construct a conic bundle.
I tried to, but I failed.
Ah, okay.
Sorry.
Okay.
I tried to, but I failed. But, so that's the question.
So here you assume that such conic bundle exists to derive properties, subsets. At least the goal is to
Yes,
construct
the goal is that. The goal is that. Yes. Okay, so now we finished the discussion of the cyclic group, and of course the next simple group is abelian groups, right? Abelian groups is like we proved this thing.
Ask another stupid question.
Oh, yeah, sure.
So you want to construct example when this group acts as a Galois, right?
Yes.
But equivalently, you can do the same just for the geometric action. Yeah.
Yes, yes. Actually, it's the same.
But maybe this is easier.
But I want Galois.
Geometrically more restrictive.
Geometrically more restrictive, but on the other hand, you can just write down equations and some way to project spaces.
Galois is inverse Galois.
Yes, Galois, you have more freedom, but this is an ABV. But you want Galois.
I want Galois. So I'm gonna give you a question at very last. Okay. So the proof of this proposition based on this short stack sequence, and I do induction on the generator of these finite abelian groups. So you have this decomposition here. In the middle part is what we want, and previously is hi times h 1 minus I. So either one of them is H1, which is trivial by the assumption. And in the torsion part, like we have H0, H1, and H2. So you have H0 paired with H2, but the H0 is a G invariant part of, of a free Z module, which is also free. So that will kill this torsion part. And for H1, which is trivial, so that will also kill this torsion thing. So which means this is zero, that forces the middle term goes to 0. Okay. So let's go back. From this first homology decomposition.
Can you go back?
Yeah, sure.
And,
Because here,
okay.
for any generators,
Yes.
for any generators, for all group elements. Okay, so according to the previous the cohomology composition, we know that the cohomology of a group only depends on the cohomology of the solo two subgroups. So, for example, if the solo two subgroup is simple, it's cyclic or abelian, then we have control on it. And furthermore, I find there are 4 families of groups whose solo two subgroups is D4. And well, what about the subgroups of D4? They're like C4, C2. That's they're all or and they're or C2 times C2. They're either cyclic or abelian, and I only need to show this. But I know their representations. I managed to show this. So finally, I got 24 families or groups satisfy this H1 uniformity. But unfortunately, those 24 families does not cover all numerical results because I have guessed some families, but when the parameter of such family increase, the solo two subgroups of such family will, the structure gets complicated rapidly, and I lose control of their H1. So this is furthermore that I mentioned that by Shepard-Barron, they show that for such conic bundle, if you just multiply A2, you can still manage to show this is rational. Okay, and here is a example that I want to show you. For example, let's go back. It doesn't work. Okay. Okay, now it works. Okay, for example here, in graph of D6, we have such D62, D5, D5 group. Okay, so S3, we have simplest one, and next was D5. Oops. So like for example, I pick example that this polynomial has Galois D5, the discriminant is -47, and the split is group is D5, and I just construct a torsor and try to show that torsor is rational. Okay, but I end up with something like this. So here, the coordinate YZ, you want to U5, we want to V5, so that's why we stay in P11 and have to solve it. Yesterday I said it's 5, but actually it's 4. Okay, so it's 4. So this is first one, it's the second one, and the third one. And
who is better?
Who is better? Well, that's a good news actually. If someone can manage to show this rational, we'll find another example.
Is it smooth? Check. Just put into Mongo.
Yeah, put it into MATLAB. The MATLAB told me maybe I should try it maybe after. But, yeah, so this is the example that I don't know how to deal with it, and I'm pretty sure like it contains a P1. No, I think yeah, it contains P1, but contains a P1 does not really help here. I think
P1.
P1, but we need more, right?
You can just place brute force. For example, the first equation is in U1. You can get rid of U1.
Yeah. Okay. Yeah. That's the equation. That line is given by like except u1, v1, the rest variables, or you all set them to 0. That's the p1. So that's why you use one equation to get rid of one. That's fine. But it gets crazy. Okay. Okay. I think this is what I want to talk right now. Okay. I just try to speed up. I don't know. Good. Any questions?
Questions?